Welcome to The Explainer. You ever wonder how Netflix just knows what movie you want to watch next? Or how scientists can sift through mountains of genetic data? Well, a lot of the time, the magic behind the curtain is a technology called Apache Spark. And today, we're going to pull that curtain back and see exactly how it works. All right, let's start with a thought experiment. Imagine you've got a 1 gigabyte data file. I mean, it's big, but it's not crazy big, right? Your personal laptop could probably handle that, chew through the analysis without breaking too much of a sweat. But what happens when that file gets 1,000 times bigger? We're talking a full terabyte now. Suddenly, your poor laptop isn't just slow, it's completely useless. It would just grind to a halt. A single machine is just not going to cut it. And this exact problem, this massive scaling issue, is precisely why Spark was born. So you get to a fork in the road. You could go with vertical scaling, which basically means building one giant, incredibly expensive supercomputer. Or you could choose horizontal scaling, where you get smart and link a bunch of normal computers together to work as a team. Spark is all about that second option, horizontal scaling. It's what we call a distributed computing engine. Now, the easiest way to think about it is this. Imagine connecting every single computer in a university library and telling them all to work together as one giant, powerful brain. That right there is the core idea behind Spark. Okay, so how in the world does Spark manage this whole team of computers? It uses something called a driver worker architecture, which really acts as the central command for the entire operation. Let's just follow the process step by step. First, you submit your code to the driver node. Think of this as the orchestra conductor. The driver looks at your code, figures out a plan, and then goes to the cluster manager and asks for the resources it needs. The cluster manager then brings in the worker nodes. These are the actual musicians, to do all the heavy lifting, processing little pieces of your data all at the same time. Now, that architecture is really clever, but it's not the only reason Spark is famous for its speed. The real magic, the secret sauce, comes down to two key ideas. You could almost call them its superpowers. Superpower number one, in-memory computation. So why is this such a huge deal? Well, its predecessor, a tool called Hadoop, was constantly reading and writing data to slow, old-school hard drives. That's like having to run to the library to look up a new fact every single time. Spark, on the other hand, keeps all the important data right in RAM, the computer's super-fast short-term memory. It's like having all the books you need open on your desk right in front of you. This one change can make it up to 100 times faster. And superpower number two is called lazy evaluation. And honestly, this is brilliant. Think of a chess grandmaster who plans out the entire game 10 moves ahead before they even touch a single piece. Spark does the same thing. It doesn't just blindly follow your instructions one by one as you type them. For instance, you could tell Spark to do a bunch of things to your data. We call these transformations. Things like, hey, select only these specific columns, or filter out any rows that don't meet this condition, or maybe add a brand new column based on a calculation. But instead of doing each one right away, Spark just listens. It bundles all of your requests together, and then it analyzes them to find the absolute most efficient way to get you what you want. This is a game changer because it might find incredible shortcuts, like combining two of your filters into one single step, which saves a massive amount of time and effort. And get this, absolutely nothing actually happens until you finally trigger what's called an action with a command like .show. That's the signal to Spark that says, okay, I'm ready for my result. Go. And only then does it execute its perfectly optimized plan. So that's the theory, but what does this actually look like when you're tapping away on a keyboard? Let's take a quick peek at a few lines of PySpark, which is just the super popular way of using the Python language to talk to Spark. So first things first, you've got to read some data. Here, we're loading a CSV file into a special structure called a data frame. The best way to picture a data frame is as a giant, super smart spreadsheet that's spread out across all those computers in your cluster. Next, you apply a transformation. Here, we're telling Spark, out of this whole giant table, I only care about two columns, item_type and item_MRP. Now remember, at this point, Spark has just made a note of your request. It's being lazy. It hasn't actually done anything yet. And nothing runs until you call an action. That .display command, that's the trigger. The second Spark sees that, its whole optimized plan roars to life, the workers get to work, and then boom, the final result, Just those two columns you asked for appears on your screen. So when you put it all together, the distributed computing, the in-memory speed, the lazy planning, why is this whole thing such a massive game changer for data? Well, it's because Spark basically democratized big data. It took the incredible power of supercomputing, which used to be something only a handful of huge organizations could afford, and made it accessible, fast, and efficient for almost anyone. It allows us to ask and answer questions on a scale that was just science fiction a couple of decades ago. And really, that's the bottom line. That transformative power, the ability to find a needle of insight in a haystack the size of a mountain, is why Apache Spark is still one of the most critical and sought-after technologies in the entire world of data. The only question left is, what are you going to build with it?